Have you ever wondered what makes one radio tune in perfectly while another struggles with interference, or how some circuits can precisely isolate a single signal from a sea of noise? It all comes down to a crucial characteristic of resonant circuits. The Q factor, or quality factor, is a fundamental parameter that directly defines a circuit's bandwidth and selectivity. Simply put, a higher Q factor indicates a narrower bandwidth and greater selectivity, meaning the circuit is better at distinguishing a desired frequency from others. This relationship stems from how a resonant circuit handles energy. The Q factor is mathematically expressed as the ratio of energy stored in the circuit to the energy dissipated per cycle. A circuit with a high Q factor stores a lot of energy and dissipates very little, leading to a very sharp peak in its frequency response. This sharp peak corresponds to a narrow bandwidth. Conversely, a low Q factor implies more energy dissipation, resulting in a broader, less defined peak and thus a wider bandwidth. This efficiency in energy management is why Q factor is so critical. Understanding the Q factor empowers engineers to design circuits for specific applications. For instance, in radio receivers, a high Q factor is essential for the antenna tuning circuit to pick out a specific broadcast frequency without interference from adjacent stations. In contrast, if you need a circuit to respond to a wider range of frequencies, such as in an audio equalizer, you would intentionally design for a lower Q factor to achieve that broader response. By adjusting components like resistance, inductance, and capacitance, we can precisely control the Q factor. Another interesting detail is the concept of the damping factor, which is inversely related to the Q factor. A high Q circuit corresponds to a low damping factor, meaning oscillations will die out slowly. Conversely, a low Q circuit has a high damping factor, causing oscillations to decay rapidly. The Q factor is a dimensionless quantity, making it a universal metric for comparing the performance of different resonant systems, from electrical circuits to mechanical resonators. Ultimately, mastering the Q factor provides you with the key to fine-tuning a circuit's frequency behavior. It enables you to achieve either razor-sharp precision for filtering and oscillation stability, or a broad, encompassing response for wider signal processing, ensuring your designs perform exactly as intended for a diverse range of electrical engineering applications.